Right now, somewhere in South Korea, a sheet of glass thinner than your fingernail is about to become a window into another world. This is not ordinary glass. This is the most sophisticated surface ever created by human hands. And over the next 15 minutes, you will witness something fewer than 1,000 people on Earth have ever seen: the complete transformation of raw sand into a 110-inch OLED television, pixel by perfect pixel. What you are about to experience cost $10 billion to make possible. Not the television, the factory. Welcome to the bleeding edge of human manufacturing. Welcome to the OLED Megafactory. Before dawn breaks over the city of Paju, a specialized truck approaches a building that stretches longer than 3 football fields. Inside that truck, suspended in climate-controlled silence, rests a cargo more valuable than gold by weight: Gen 10.5 mother glass. Each sheet measures nearly 11 feet by 10 feet, yet weighs less than a small child. At just 0.7 millimeters thick, this glass could slice through paper, yet it must survive a journey through 127 processing steps without a single scratch, crack, or microscopic fracture. The truck seals against the loading dock with surgical precision. Positive air pressure floods the connection point. Not a single particle of outside dust can be permitted entry. What happens next occurs in an environment cleaner than an operating room, cleaner than a pharmaceutical laboratory, cleaner than anywhere you have ever been in your entire life. This is a Class 100 clean room. That number means there are fewer than 100 particles larger than half a micron in every cubic foot of air. For comparison, the room you are sitting in right now contains approximately 35 million. The glass now floats, literally floats, on a cushion of filtered air so pure it has been scrubbed of 99.999% of all contaminants. This air-bearing technology allows the massive sheet to glide through the factory without ever touching a solid surface, eliminating the primary source of glass damage in traditional manufacturing. But first, inspection. Automated optical systems scan every square millimeter of the substrate surface. They are searching for defects invisible to the human eye, imperfections measured in nanometers, 1/1000th of a meter. A single contaminating particle the size of a bacterium would doom an entire television panel. The glass that passes inspection enters a washing sequence that borders on ritualistic. Ultrasonic waves create millions of microscopic bubbles that implode against the surface, blasting away particles through a process called cavitation. The same physics that allows pistol shrimp to stun their prey is now cleaning your future television. Deionized water, stripped of every mineral and impurity, until it becomes one of the most aggressive solvents on Earth, cascades across the pristine surface. This water is so pure that it will actually pull ions from your skin on contact. Factory workers never touch it with bare hands. Now the transformation begins. The glass enters a vacuum chamber, where the air pressure drops to 1/1,000,000th of normal atmospheric levels. At this pressure, you could not survive for 3 seconds, but for creating thin film transistors, it is absolutely essential. Plasma ignites. A ghostly purple glow envelops the massive glass sheet as charged particles rain down upon its surface, depositing atoms one layer at a time. This is LTPO technology, low-temperature polycrystalline oxide, and it represents one of the most significant advances in display science of the past decade. Each transistor being formed right now is smaller than a human red blood cell, and there will be over 100 million of them on a single panel. If you counted 1 transistor per second, it would take you more than 3 years of continuous counting to reach the total. The precision required here defies imagination. Layer thickness must be controlled to within a single nanometer. That is the width of 10 hydrogen atoms placed side by side. Variation greater than this would cause visible defects in the finished display. Photolithography follows. Intense ultraviolet light projects circuit patterns through masks, containing features smaller than the wavelength of visible light itself. The physics that makes this possible were thought to be impossible just 20 years ago. Engineers had to essentially hack the laws of optics to make modern displays viable. Everything until now has been preparation. The backplane is merely the canvas. Now we paint with light itself. The glass substrate, now embedded with millions of transistors, enters the most sophisticated vacuum chamber ever constructed for display manufacturing. Pressure here drops even further, approaching the emptiness of outer space. In this near-perfect void, organic molecules will perform their magic. These molecules are the heart of OLED technology. When electricity passes through them, they emit light directly, with no backlight needed. The result is perfect black, because pixels that are off produce zero light. Not dim light, zero light. This is why OLED blacks look like infinite darkness, because in a very real sense they are. But here is where it becomes truly extraordinary. This factory does not use white OLED with color filters like other manufacturers. This is RGB OLED, where red, green and blue subpixels are deposited individually through fine metal masks, positioned with nanometer precision above the substrate. Imagine spray painting through a stencil, except the stencil has 8 million holes, each one smaller than a grain of pollen, and the paint is a vapor of organic molecules in near zero gravity conditions. Get the alignment wrong by the width of a human hair, and you have just destroyed a panel worth more than a luxury automobile. The organic materials themselves are among the most closely guarded secrets in the technology industry. Their exact chemical compositions are known to perhaps a few dozen scientists worldwide. What we do know is that they are carbon-based, making OLED displays technically organic in the same way that you and I are organic. These televisions are, in a sense, alive with chemistry. Organic molecules have a fatal weakness: moisture. A single drop of water vapor invisible to the naked eye would destroy an OLED panel within hours. The light-emitting layer would oxidize, turn dark, and die. The solution is encapsulation so complete that it approaches hermetic perfection. Alternating layers of organic and inorganic barrier films seal the OLED stack from the outside world. These barriers are deposited atom by atom using a technique called atomic layer deposition, building protective walls just nanometers thick, but capable of blocking moisture for decades. The Gen 10.5 mother glass can yield multiple large format panels. Laser scribing systems trace precise cutting lines across the substrate, their beams focused to spots smaller than a human hair. The glass does not shatter or crack. It separates cleanly along mathematically perfect lines, yielding individual 110-inch panels ready for the next phase of their journey. Each panel edge is then polished to optical perfection. Diamond-coated wheels remove microscopic fractures left by cutting, because even invisible damage could propagate into catastrophic failure months or years after installation in your home. A display panel without electronics is merely an expensive piece of glass. The next stage gives it a brain. Along the panel edges, workers bond chip on film packages containing driver-integrated circuits. These tiny chips translate video signals into the precise voltages required to illuminate each of the 33 million subpixels. The bonding process uses anisotropic conductive film, an adhesive containing microscopic metal spheres that create electrical connections only where pressure is applied. The precision required here is measured in microns. Each bonding pad on the panel must align perfectly with its corresponding connection on the driver chip. A misalignment of just 50 microns, half the width of a human hair, would render the entire panel defective. Thermal management comes next. OLED panels generate heat, and heat accelerates organic material degradation. Graphite sheets capable of spreading thermal energy laterally across the entire panel surface are applied with painstaking care. These sheets can conduct heat 3 times more effectively than copper, while being lighter than paper. The panel mounts into a precision-machined aluminum frame that serves dual purposes: structural support and heat dissipation. Every mounting screw is torqued to exact specifications. Too loose and the panel could shift during transport. Too tight and stress could crack the glass months later during temperature cycling. Power supplies, main processing boards, and kilometers of internal cabling transform the framed panel into a functional television. Workers in full cleanroom protective equipment route cables through designated channels, securing them against vibration and electromagnetic interference. The attention to detail here would satisfy aerospace engineers. The television powers on for the first time. After weeks of processing through more than 100 individual manufacturing steps, the panel illuminates. Pure white light floods the calibration bay as all 33 million subpixels activate simultaneously. In this moment, factory technicians witness something closer to birth than assembly. But birth is just the beginning. Now comes education. Every OLED panel, due to the organic nature of its light-emitting materials, has subtle variations in brightness and color across its surface. Left uncorrected, these variations would appear as blotchy, uneven images. The solution is individual pixel-level calibration, a process where every single subpixel is measured and corrected. Spectroradiometers measure the exact color coordinates produced by the panel. The data feeds into algorithms that generate correction profiles stored permanently in the television's memory. This is why two identical model televisions from this factory can display colors that match to within tolerances invisible to even trained human eyes. Each television knows its own imperfections and compensates for them automatically. The panel then enters a 48-hour burn in stress test. Continuous operation under elevated temperature conditions accelerates the initial stabilization of organic materials. Defects that might take months to appear under normal use reveal themselves in hours under these conditions. Only panels that emerge unchanged proceed to final assembly. A 110-inch OLED panel represents perhaps $30,000 of manufacturing investment. Damaging it during packaging or shipping would be an expensive tragedy. The protection systems engineered for these televisions rival those designed for transporting fine art. Custom molded foam corners absorb impact energy from any direction. Inner fabric sleeves cushion the panel surface while allowing static electricity to dissipate safely. The exterior cardboard containers are engineered with specific crush resistance profiles, strong enough to survive stacking, yet designed to collapse progressively in a severe impact, sacrificing themselves to protect the treasure within. Multiple boxes stack onto pallets in precisely calculated configurations. Engineers have computed the exact weight distribution required to prevent bottom boxes from crushing under the combined load. Stretch wrap binds everything into a single stable unit capable of surviving ocean shipping, air freight, and the unpredictable violence of ground transportation. The loaded truck pulls away from the factory dock, carrying televisions to destinations across the planet. Some will end up in Tokyo penthouses, others in Los Angeles home theaters, a few in Dubai mansions and London townhouses. But every single one began its journey here, as nothing more than sand, purified into glass, transformed by plasma, painted with organic light, and assembled by hands that understand they are creating something unprecedented in human history. 110 inches of perfect darkness and infinite color, 33 million points of self-illuminating beauty, $10 billion of engineering made manifest in your living room. This is how massive screens are built. This is the OLED Megafactory. And the next time you watch this screen, remember, you are looking through a window that took humanity 50 years of scientific advancement to learn how to open. What will you watch first?